Okay, good morning, everyone. Welcome to the first talk of this session. The speaker is Muharem Avdispahic from University of Sarajevo. He's an expert in number theory and is going to talk on Selberg's trace formula, Hilbert's constant, and the Faltings state function. Okay, please join me in welcoming our first speaker.
Thank you for coming. I would like, of course, to thank Professor Yao and the organizing committee for the invitation, for the wonderful hospitality. I believe you hear me. Yeah. It was a memorable experience, ICM 2002 in Beijing, and many of us are looking forward to the success of Shanghai 2030. Actually, Shanghai was the place where at the IMU General Assembly, Boston Mathematical Society has become a member of the International Mathematical Union. I saw on the T-shirts, it's written not only International Congress of Basic Science, but Truth and Beauty. So during the lifetime of my generation, is it okay? Yeah, thank you very much. Thank you very much. During the lifetime of my generation, the understanding or the comprehension of the character of number theory evolved from Hardy's viewpoint that number theory was the purest part of pure mathematics, and in his words, to qualify as pure, the mathematical topic had to be useless. If useless, it was not only pure, but beautiful. Now, from that point over, of course, undreamable applications in computer science, especially cryptography, to what Bolovich would say number theory as the ultimate physical theory. So quite in spirit of the conference. The single paper of Riemann, as you know, marked the birth of analytic number theory. And nowadays, not only mathematicians, but what physicists say about it. You have Polish cosmologist Maslanka. All mathematics is beautiful, yet some is more beautiful than the other, but the most beautiful mathematics is the zeta function. And on the line of Hilbert and Polya, ideas, we have now physicists saying that a variety of evidence suggests that underlying Riemann zeta function is some unknown classical mechanical system whose trajectories are chaotic without time reversal symmetry, with the property that when quantized, its allowed energies are the Riemann zeros. These connections between the seemingly disparate worlds of quantum mechanics and number theory are tantalizing. According to Henri Weil, number theory, geometry, finite fields are three languages of the Rosetta Stone of mathematics. And we witnessed something of that already in quite a number of talks these days. And also this Bombier, this view on motifs, Galois representations, and automorphic forms as Rosetta Stone of our functions. Of course, the Riemann's paper was about distribution of prime numbers. It occupied attention earlier by Gauss, by Dirichlet. Chebyshev introduced two functions known, bearing now his name, which are more suitable for analysis than the prime counting function. And the theorem the prime number theorem was finally proved independently by Adamar and Delavalle-Poussin by showing that Riemann's zeta doesn't vanish on the line real part of S equals 1. And back to other way, one would be totally abstracted if there were not a bridge between number theory and Riemann surfaces. So the stage for this talk is set actually by upper half plane with hyperbolic metric and hyperbolic area. We see here geodesics. These are some triangles with geodesic sides, and Möbius transformations are conformal orientation, preserving isometries of the upper half plane, mapping geodesics to geodesics. Fuchsian groups are discrete subgroups of PSL2R, and they can have finitely many elliptic subgroups which are finite themselves, then finitely many parabolic subgroups which are infinite themselves, and infinitely many hyperbolic subgroups. When we look at the hyperbolic element, it is diagonizable over R2 unique matrix, and the larger eigenvalue is the norm of P, and for every P there is primitive hyperbolic P0 such that P is the nth power of P0. And what is important is the connection or the relation between these hyperbolic classes and primitive closed geodesics on the surface. If, as it is written here, the length of the primitive closed geodesic is actually logarithm of the norm, and in case the gamma is strictly hyperbolic, we have compact Riemann surface. Prime geodesic theorem says the same, roughly the same thing as a prime number theorem, that when you count these primitive hyperbolic classes with the norm less or equal x, then it's approximately logarithmic integral at x. Selberg introduced also the function which is now bearing his name, convergent in the right half plane, real S larger than 1, and meromorphically continued to the whole complex plane. What is important is that the Selberg zeta on Riemann, on compact Riemann surfaces, satisfies analog of Riemann hypothesis. So the non-trivial zeros, they correspond to the eigenvalues larger or equal 1,4 of the essentially self-adjoint Laplace operator over there. Now, a long time ago, so at the beginning of last century, von Koch showed that Riemann hypothesis is equivalent to the statement that the error term in prime geodesic theorem is of the size x to 1/2 plus epsilon, or more precisely x to 1/2 log x, or in terms of Chebyshev function, or x to 1/2 log x squared. However, so we have an analog of Riemann hypothesis satisfied the setting I'm talking about. It is outstanding open problem whether the error term in prime geodesic theorem is of that corresponding size. And what is the obstacle? The obstacle is the different density of zeros. So in Riemann zeta is a function of order 1. If you count these zeros on the critical line up to level t, you see that the size is log squared of t, and in Selberg zeta case, it's constant times t, so much denser. What is the Huber constant? Well, Huber was the one who gave an asymptotic estimate of the error term in prime geodesic theorem, because Selberg just proved the theorem itself wasn't so much interested in the error term. So Huber actually showed that this difference, so pi over x minus logarithmic integrals corresponding to these small eigenvalues, that error term can be bounded by x to 3/4 over square root of log x. Subsequently, Randall improved that result to x to 3/4 over log x. And in general case, it is the best what we have at the moment. So Huber's constant is defined not only for compact, but for cofinite Fuchsian groups as the smallest constant in the prime geodesic theorem on the orbifold h over gamma, such that this error, this difference can be controlled by that constant times x to 3/4 over log x. But what is important here is this for all x larger than 1. So when you look just approximately as x tends to infinity, the situation is different in some special cases, but we are interested in the constant which will satisfy this condition for all x. I'm just showing the slide with the final wording of the theorem. So if gamma is a cofinite Fuchsian group, then Huber constant is controlled by such an expression. We will come later to some details, but this depends, of course, on the size of the shortest closed geodesics, this Lx, which you see, which you see here. So we have different precision of estimates depending whether Lx is smaller or equal to 4/3 than, or in this interval of that, or larger than h3. But if you just look at these indices, 22 or something, these are the constants, the effective constants which we'll get, but that shows that there are many steps to come to that point. And even I haven't dared to put a slide. It could not be set on one slide, the whole algorithm, which is to be followed. First, why such thing is relevant? Well, when considering the analytic aspects of a Rakelov theory or algebraic curves, then one is interested in bounds for special values of Selberg's zeta functions, or Green's functions, or Faltings delta function. Some fundamental constants, that's the table which I did include. We have, as I said, cofinite Fuchsian group with a finite area, this F. Then the cusp sector, the hyperbolic diameters, this theta Amer values, which you see that is for elliptic classes. This italic A is number of small eigenvalues, and is number of poles of scattering determinant in that interval 1/2, 1. Lx, which we already met, is the length of the shortest closed geodesic. C is E, the infimum of norms, it is e to the Lx. And these are also some integrals which come into play when calculating these things. So the basic tool is Selberg trace formula. Essentially, it is, one could say, only available tool to study the spectra of Laplace, Beltrami Laplace operator. On the left hand, you see some test function h, and on the left hand side of this formula, we have values of that function, of test function at spectral data. Left hand side means up to the sign of equality, and on the right hand side are values at geometric data. Here, test function is even holomorphic function in that strip, satisfying the growth condition imposed by Selberg, and G, which is here in the which is here in the formula, is actually the Fourier transform, and that capital Phi is matrix of the scattering matrix, and psi in the formula is the logarithmic derivative of the gamma function. In the first part of calculation, one uses concrete test function e to the tr squared to get an upper bound for the implicit constant in the spectral counting function. So you count these the discrete the part of the discrete spectra up to this level which is written there, and the part of continuous spectra. And the spectrum for the other, so that basically there are two stages. In the first stage, one uses this test function, and in the other, we will see the other one. So, first, looking to the geometric side of that formula, if I should go back, so we see many terms on the right-hand side. So, contribution of the identity term, at this moment we control by some function a1 of t. The parabolic term is controlled by the function which you see in this fourth line from the bottom. For the elliptic term, we also have this a3 of t, and to estimate the hyperbolic term, one uses first this rough estimate of the prime geodesic counting function, where y and dj were in the list of the fundamental constants, and b1 is formed from that. And then we get that this is controlled by what you see in the second line, and what is denoted as A40. So when you put all these in, you get that the left-hand side is dominated by the sum of these four functions already mentioned. Okay, just to understand the two slides above. So now we will make use of a quantitative Karamata-Tauberian theorem. So alpha is a non-negative, non-decreasing function, continuous on all but a possibly countable subset of 0 infinity, taking alpha at 0 is 0, and so sorry for that. Here is actually the equality sign missing. So this f of s, this integral converges for all s larger than 0. And we suppose that f of s is controlled by constant over s on the interval between 0 and some d. Under these assumptions, we get actually the estimate of on alpha itself, that this function alpha is controlled by e times this constant times t on the interval from 1 over d to d will be 4, because 1/4 is actually, we have, till 1/4 we have this small eigenvalues and this part to the right. So that will now explain why one replaces the signed function appeared in that trace formula. Signed real function we replace by this function, logarithmic derivative of it, we replace by this one where we actually included poles of this scattering, determinant in the interval 1/2, and then we control the effect of that replacement. This is now some function of t, and with then after saying that, the new version, not the new version, but we can say that the left-hand side from the formula, when you with this logarithmic integral of phi n is controlled by some a7 t. So far, all these a's were functions of t. With n lambda, it's the number of discrete eigenvalues up to level lambda, and q lambda is that part of corresponding part of continuous spectra. And now you recognize that situation where we have integral a to minus t lambda, this n of lambda plus q of lambda is actually this alpha in Karamata-Tauberian theorem. So that's the point where we will use that theorem. So we would like to not to deal with functions of t, but actually to come to concrete constants a1 to a7, which will give us this condition required by Karamata-Tauberian theorem. And of course, there are long and heavy calculations, but in some of the parts, some are very easy. So the numerical constants A1 is the volume of the fundamental domain over phi pi. A2 is what you see there, coming from parabolic elements, A3 from elliptic elements. Then it is important, one of the steps in the proof is important to control this function ta3 of t over e to t fourth. There is precise bound for that. So finally, we get that this number of discrete eigenvalues up to level L plus that part of continuous spectrum is controlled by E times this numerical constant A7 times lambda. So I said that first we look at how to control the spectral counting function. So this is the growth of the spectral counting function, and we have precise numerical value for the constant k. Yeah. Just for information, and if you do this also for the modular group PSL2Z, these calculations will give you a constant of the size, let's say 4 times 10 to 4 now. For PSL2Z, we will meet it again several times during the talk. You see its fundamental domain, but in case of such groups which do possess some additional properties, one can say, of course, more. And the closed geodesics on modular surface, they correspond to regulators of real quadratic fields. The multiplicity equals the class number, and so on. So I said that in the other part of the proof, we need now another test function. We start with this phi of x, which is e to 1 over x squared minus 1. And so it is, as you know, infinitely differentiable and supported in the closed unit interval. The value at 0. And it is normalized so that the value of its Fourier transform equals 1. And then we take in the usual way the form approximate identity phi epsilon. And the test function now is actually this h epsilon t. And it is the Fourier transform of the convolution of this approximate identity with the characteristic function of the interval times this cosines hyperbolic. And the task ahead is now to give explicit estimates in the Selberg trace formula when this test function h e t is plugged in. You just check. So somewhere in the formula we have this capital H E T, so this is what the meaning. And we proceed in counting explicit constants which would control the steps we need to make. So when we look at the sum of small eigenvalues, it differs from this sum of x to Sn over Sn by this constant A11 times 6 to 3/4. The rest for lambda bigger than 1/4 is controlled, the constant which is involved is again very explicit one. That part which correspond to identity term is also, we now have 18, we have a 14 to control the elliptic, the contributions from the elliptic parts, A15, and so on. In the last proposition shows how this capital H, to which extent it differs from that sum over small eigenvalues. What we had here is H corresponding to that epsilon test function, let's say that. Now, of course, we need the real H and control the difference between the two, control the difference between this real H of X and the sum of small eigenvalues. And that's the point when Chebyshev functions come into play. So again, we look how much the Chebyshev function at X differs from this Hx. The Chebyshev function of the first and second Chebyshev functions, so both of them. And so we are already at the index 21. The final steps in the proof. So the counting function is logarithmic, is Stiltes integral over d theta over log y. Then we split it in, this theta gamma minus the difference of the corresponding to small eigenvalues is denoted by Fy. We have already the bounds which are necessary there, and we get actually that we get the final constant which is needed, A22. So and all these relations combined, they give us what was stated in the theorem. And many of these propositions are proved under the assumption that X is larger than the infimum of the norms. But since we need the bound for all X, then one also has to check that on the interval 1 to C, the same bound will work, which we calculated. So when it comes to Faltings delta function, then some of the preliminaries are the hyperbolic heat kernel for functions on H, for functions on the corresponding Riemann surface, and we have the averaging over gamma. And that the Faltings delta function is, as some of you know, an important invariant associated to this compact Riemann surface. And J. Jorgensen and Jürg Kramer in Annals of Mathematics in 2009, they succeeded to express this faulting through purely hyperbolic terms. That was sufficiently worse result to be published in the Annals of Mathematics. To constant involved there f of z which appears in this integral. It is, well, as I said, we have now the bound for that constant. We have the bound for limit between this pole and the logarithmic integral of z, the bounds of logarithm of the derivative of z, and as far as the first line is concerned, s of x is actually this expression we have supremum between of the ratio between canonical and hyperbolic measure. Gx appearing there is genus of the surface. We end up with this bound for Faltings delta, and if you look at that, you see that in the third line on the right, you see that Huber constant is involved. So the calculation of Huber constant is important to have the final effective bound for Faltings delta. So if X is a compact Riemann surface of genus larger than 1, such that the length of the shortest closed geodesic is larger than 4/3, this is the bound for Huber constant. So as look what is involved, it's actually the genus and the shortest geodesic. So in this particular case, when L of x is larger than A3, then we have a smaller bound. So now, if x happens to be unramified covering of finite degree, where x0 is a compact Riemann surface of genus gx0 larger than 1, and with a length of the shortest closed geodesic larger than 4/3, we get the estimate for delta Faltings, which is less sorry, the constant which appears here, Cf, is less than 10 to 7, and this is what I actually proved there, gives us a bound which is reduced by factor 10 to the 8 to previously claimed one. It is also worth noting that that previously claimed one was not actually proved because there was a flaw in the proof itself. But if it were true, it were 10 to the 8 times bigger. In a particular case, then this x0 can be covered by a modular curve for the full congruent subgroup for some n, then we get this bound, and in that case the reduction is even to 10 to 16th power. So when it comes to triangle groups, well, we are speaking about triangles whose sides are parts of geodesics with the angles 1 over p, 1 over p over pi over p, pi over q, pi over r. So why I put this here? Because in the theorem about Huber constant, there were 4 cases. So these are illustrations for some of these cases. So if we have 2, 3, 7 triangle group, then we get this bound for Huber constant 950 times 2. If we take 3, 3 infinity, so that is the shortest figure 8 geodesic on a triangle group polyfold with 1 puncture. We know its length, it belongs to that second interval which I was mentioning, and we use then the corresponding bound in that case. And third example, 2 infinity, infinity, orbifold with the shortest figure 8 geodesic length. There are 2 punctures, and that is covered by the third of the options. Some of you probably met with that book, The Eightfold Way, The Beauty of Klein's Quartic Curve. And in the case of Klein quartic, we get this estimate for Faltings delta function. Okay, up to now I was speaking of what was the main part of the talk, this effective bounds for Selberg zeta and Faltings delta function. And as I said, the important point was that the bound should be valid for all x larger than 1. When it comes to approximate bounds, to bounds when x tends to infinity, then, as I said in the very beginning, we are targeting for optimal order in prime geodesic theorem. Up to now we have this x to 3/4 over log x in general case, but what could be said in some special cases. So, speaking about modular group, modular surface, it seems that every 10 years we have improvements. So Ivanets was the first one to break that 3/4 barrier, replace it with 35 over 48. So 11 years later, Luo and Sarnak obtained 7 over 10. Kai, a little bit better, 71 over 102. Soundarayan and Young in 2013, 25 over 36. And there is a paper on archive where Kaneko reached 2/3 in case of modular. When it comes to dimension 3, we are speaking about upper half space. Again, we have the corresponding hyperbolic metric, hyperbolic volume element, Laplace-Beltrami operator, the group of orientation preserving isometries acting transitively. Its subgroups are now called Kleinian groups, and in this case, trace doesn't have to be real. So if it is real, the classification is between hyperbolic, parabolic, and elliptic elements as before. In all the other cases, we speak of loxodromic, and every hyperbolic or loxodromic P is conjugate to a matrix of such a form, and the norm is again the square of the larger value of the larger value, and P is the power of primitive. So, and we consider compact or non-compact finite hyperbolic manifolds. The corresponding Selberg zeta function, which satisfies, in compact case, which satisfies this functional equation. Again, we have discrete spectrum, and now the critical line is not 1/2, but 1. And we look at the zeros lying in the interval 1, 2. We have the while, so on the size of the number of eigenvalues up to 1 plus 2 squared, t squared is what you see there, and the corresponding Chebyshev function. The exponent which one expects in this case, ideal exponent, would be x to 1 plus epsilon. One has x to 5/3 over log x, and Sarnak obtained that for in case of PSL over rings of integers. In higher dimensions, this is how the result looks like. I proved it with my PhD student, and the bound coincides with the obtained ones in case of dimension 2 and dimension 3. And what is important here, that Selberg zeta is not sufficient for this. You need Ruelle zeta function. There are also conditional improvements. Well, the first one, Ivanet's explicit formula, is not only for conditional but for his unconditional results. He proved that explicit formula and used it to get to what we said, 35 over 48. Gallagher, let me just. So in 1980, Gallagher actually proved that under Riemann hypothesis, the error term wouldn't be only x to 1/2 log x, but log x squared, outside the set of finite logarithmic measures. So we are now speaking of some of the results under such a condition, but to prove that he actually proved the lemma which is in the middle of the screen. So S of u is the absolutely convergent series which you see there, and then the integral of as u squared from, let's say, minus v to v is controlled by what you see on the right-hand side, pi theta over sine of pi theta, and under the integral v over theta, and we are integrated over t. What is t? Well, we look at that portion of the sum of coefficients which lie where indices are between t and t plus theta over v. And there is also a very useful result by Balkanova and Frolenkov on the control of the sums of the type x to y, gamma up to level y. What is interesting here, that for the first time we have the x to 1/2 appearing in the error term, but under two conditions. The one is what, I mean, many of you know that there is a big 2-volume books by Dennis Heyhal, the Selberg trace formula, and at one point he considers this function as gamma, the argument of Selberg zeta on the critical line, and the condition of its integrability. So under assumption that this S gamma of t over t is integrable, is in LP for some p between 1 and 2, then one can get this x 1/2, and again, not only under that condition, but we can get that outside of a set of finite logarithmic measures. Without that integrability assumption, Balog, Biro, Harkosh, and Maga, they have second moment prime geodesic theorem that would imply the bound 7/12 outside the set of finite logarithmic measures. And it is 2/3 of the way from 3/4 to 1/2. On what is also interesting, that on compact Riemann surfaces, you can get also 1/2 outside the set of finite logarithmic measure if it happens that this Heyhal's condition is fulfilled. We don't know. For non-compact cofinite case, in that Heyhal's big study, you have first compact. The first volume is about compact. Then the second volume has what he would say type, Selberg trace formula type B, and then type C. So this is the most complicated one. And there you have you have a surface with cusps, the multiplier system with a certain weight. You have irreducible dimensional unitary representation involved, corresponding Laplace-Beltrami operator, the functions which you look at, the corresponding Selberg zeta. This is how prime geodesic counting function look like in that case, and the Chebyshev function. And what we get there is 7/10 outside the set of finite logarithmic measure. On 3 manifolds, Chatsakos, Cherubini, Laxonen, through the second moment prime geodesic theorem, they obtained 3/2 plus epsilon. In d dimensions, of course, if you look outside the set of finite logarithmic measure, the exponents which appear in the error term are smaller than in the unconditional case. And just as an outline, what is the trick? You integrate the Chebyshev function up to the dimension v. Then you sum these over real eigenvalues, and then the sum over critical line. And this sum over critical line is split into three parts, up to certain level y, then from y to w, and from w above. And the first and the third are easily controlled, but to control the middle one, to control this middle one from y to w, you use these functions, where you will, the point is that the function which you integrate is non-decreasing, and that enables you to found the bound from above and from below for the function, starting from the bound of the integral. And for that second middle part, you divide your line from 1 to infinity into these parts, e to j plus 1, and see that the lower bound be such to give you the terms which in the sum will give you final logarithmic measure. And that's how you arrive what you should take as h, as y, so on, to get the result. And now just a short, well, I'm close to the end. Okay, like just 3 sentences. So we had Riemann zeta and functional equation and Riemann von Mangold explicit formula. You have Dirichlet L function. You have Dedekind zeta and Hecke L function. But what I want to say that a great number of these zeta and L functions in modern number theory, they apparently obey a certain formalism. They possess a representation in the form of Euler product over primes, be it numbers, ideals, or hyperbolic classes, and satisfies a functional equation. And that was the motive for Serge Lang and J. Jorgensen to introduce the so-called fundamental class of functions where you have a triple z tilde phi, where z tilde are meromorphic, they have this Euler sum condition fulfilled and the functional equation, and under such assumption they look at the general explicit formula. What we succeeded is to loosen the conditions at infinity, at zero, under which we can get explicit formula, and that enables us, let's say, to take, in case of the Selberg trace formula as a test function, a function which doesn't satisfy Selberg's condition. Okay, I will stop here. Thank you very much.
Any questions?
Oh, thanks for the rich talk. I wonder if there are any results on the average of the arrow terms. Could it be reached like 1/2 in average?
I'm not sure what that would mean, but I'm not aware of that kind of investigations. No papers of that kind.
No paper so far.
I mean, if you don't look at this, that something is valid outside the set of finite logarithmic measure, that's some kind of average.
Yeah. Okay. Thank you.
You're welcome.
Okay. Other questions? Okay, if there is no questions, let's thank our speaker again. Okay, we have a tea break outside. Next talk will start at 9:30.